In the summer of 1950, at a laboratory in the New Mexico desert, where scientists had split the atom and changed the world forever, a Nobel Prize-winning physicist asked a question that should keep you awake tonight. Enrico Fermi was walking to lunch at the Fuller Lodge in Los Alamos with 3 colleagues. They had been chatting about flying saucer sightings and a New Yorker cartoon showing little green men stealing trash cans in Manhattan. The conversation drifted. They sat down, and then, out of nowhere, Fermi blurted out a question that silenced the table. "Where is everybody?" His colleagues understood immediately. He was talking about aliens, about intelligent life beyond Earth, about the deafening silence of a cosmos that should be teeming with civilizations. Edward Teller, the physicist who would become known as the father of the hydrogen bomb, was at that table. So was Emil Konopinski and Herbert York. According to Teller, the result of his question was general laughter because of the strange fact that, in spite of Fermi's question coming out of the blue, everybody around the table seemed to understand at once that he was talking about extraterrestrial life. That afternoon, Fermi did some quick calculations. He estimated the number of stars in our galaxy, the probability of planets, the likelihood of life, and he arrived at a troubling conclusion. Given the immense age of the universe and the staggering number of opportunities for life to arise, we should have been visited many times over by now. The math said so, but we haven't been. No signals, no probes, no visitors, nothing but silence. York later recalled that Fermi followed up with a series of calculations on the probability of Earth-like planets, the probability of life given an Earth, the probability of humans given life, the likely rise and duration of high technology, and so on. He concluded on the basis of such calculations that we ought to have been visited long ago and many times over. 75 years later, that silence has only grown louder. We have discovered over 5,000 exoplanets. We know there are at least 300 million potentially habitable worlds in our galaxy alone. We have listened with radio telescopes spanning continents, and still, the cosmos offers nothing but static. This is the Fermi Paradox. And tonight, we are going to explore 7 possible explanations for it. Some of these solutions are reassuring, others are terrifying beyond measure, and at least one of them almost certainly describes the truth of our situation in this vast, silent universe. What you are about to read may change how you see the night sky. It may change how you think about humanity's future. It may keep you awake tonight, staring at the ceiling, wondering about your place in a cosmos that seems determined to keep its secrets. But first, you need to understand something. Fermi was not the first to notice this problem. In 1933, Soviet rocket pioneer Konstantin Tsiolkovsky had written about the same contradiction. If advanced civilizations existed, he argued, they should have visited Earth or left detectable evidence. His answer was eerily similar to what would later be called the zoo hypothesis. Perhaps we are quarantined by aliens to protect our independent cultural development. And even before Tsiolkovsky, the question lurked in the background of astronomical thought. Philosophers had wondered for centuries why, if other worlds were inhabited, we had received no messages, no visitors, no proof. But it took Fermi's simple question, "Where is everybody?" to crystallize the problem into its modern form. And in 1975, physicist Michael Hart gave it mathematical teeth, arguing that if intelligent life existed elsewhere, they should inevitably have colonized the galaxy. Their absence here was proof of their absence everywhere. The paradox has haunted science ever since. Before we dive into the solutions, you need to understand why this paradox is so disturbing. You need to feel the weight of the numbers. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Recent data from NASA's Kepler Space Telescope suggests that roughly half of all Sun-like stars have at least one rocky planet in their habitable zone. That Goldilocks region where temperatures are just right for liquid water. That means tens of billions of potentially Earth-like planets exist in our galaxy alone. Tens of billions. And this is just our galaxy. The observable universe contains at least 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars. Each of those stars may host planets. The numbers are beyond human comprehension. If you were to count 1 star per second, it would take you over 31,000 years to count just the stars in our galaxy. To count all the stars in the observable universe would take longer than the universe itself has existed by a factor of millions. Somewhere in that incomprehensible vastness, there should be other minds, other beings looking up at their own skies, asking their own questions. The sheer scale of the universe seems to demand it, and yet the silence persists. Now consider time. The universe is approximately 13.8 billion years old. Our sun is about 4.5 billion years old. That means there were stars forming, burning, and dying billions of years before our solar system even existed. If intelligent life arose around just one of those ancient stars, and if that civilization developed the capability for interstellar travel, they could have colonized the entire galaxy by now. In 1981, physicist Frank Tipler did the math. Even with technology only slightly more advanced than our own, spacecraft traveling at just a fraction of the speed of light, a civilization could spread to every star system in the Milky Way in somewhere between 5 and 50 million years. That sounds like a long time, but remember, the galaxy has been around for over 13 billion years. 50 million years is a cosmic eye blink. You could cross the galaxy 1,000 times over in the age of the universe. You would not need faster than light travel. You would not need wormholes or warp drives. Simple physics, the kind we already understand, allows for the colonization of the entire Milky Way. And yet, as far as we can tell, no one has done it. No probe has landed in our solar system. No signal has arrived from the stars. No megastructure blocks the light of distant suns. The cosmos appears utterly, deafeningly empty. There are variations on this argument that make it even more troubling. Even if civilizations do not colonize directly, they could send out self-replicating probes, von Neumann machines, named after the mathematician who first proposed them. These probes would land on asteroids, mine resources, build copies of themselves, and spread throughout the galaxy exponentially. Within a few million years, such probes could explore every star system in the Milky Way, and they would be nearly immortal, requiring no biological crew, no life support, no motivation beyond their programming. Where are these probes? We have found none in our solar system, though, to be fair, we have barely begun to look. The asteroid belt alone contains millions of objects we have never examined up close. Still, the argument stands. The galaxy should be full of artifacts, signals, evidence of intelligence, and we see nothing. So where is everybody? In 1961, astronomer Frank Drake convened a small conference at the Green Bank Observatory in West Virginia. Among the attendees was a young graduate student named Carl Sagan and a biochemist named Melvin Calvin, who would win the Nobel Prize during the conference itself. John Lilly, known for his work on dolphin communication, also attended. His presence led the group to jokingly call themselves the Order of the Dolphin. Drake's goal was to create a framework for thinking about extraterrestrial intelligence. He needed an agenda for the meeting, and he wanted to focus the discussion on the key questions. He wrote an equation on a chalkboard. It looked simple. N equals R star times FAP times NE times FL times FI times FC times L. Each variable represented a different factor: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction that develop life, the fraction that develop intelligence, the fraction that develop detectable technology, and the average lifespan of such civilizations. The Drake equation didn't give answers. It gave us the right questions. And when Drake and his colleagues plugged in their best guesses in 1961, they estimated there might be anywhere from 1,000 to 100 million civilizations in our galaxy. That was before we knew for certain that planets were common, before we understood the chemistry of life, before we realized how ancient the universe truly is. The paradox has only sharpened since then. The more we learn, the more the silence screams. Let me walk you through the Drake equation in more detail, because understanding it is essential to grasping the magnitude of the mystery. R star represents the rate of star formation in our galaxy. This is one of the few variables we actually know with reasonable precision. Current estimates suggest about 1 to 3 new stars form in the Milky Way each year. FP is the fraction of stars that have planets. Thanks to NASA's Kepler mission and other surveys, we now know this is nearly 100%. Planets are not rare, they are everywhere. NE is the number of planets per star that could potentially support life, the planets in the habitable zone. Current estimates suggest somewhere between 1 and 5 such planets per suitable star system. Here is where things get murky. FL is the fraction of habitable planets that actually develop life. We have no idea. We have exactly one example of abiogenesis, the origin of life from non-life, and we still do not understand how it happened. The probability could be nearly 1, meaning life arises almost anywhere it can. Or it could be vanishingly small, meaning Earth won a cosmic lottery. Fi is the fraction of life-bearing planets that develop intelligent life. Again, we have one example. For 3 billion years, Earth was home to nothing but microbes. Complex life emerged only in the last 500 million years. Intelligence emerged only in the last few million. Is this typical? Exceptional? We do not know. FC is the fraction of intelligent species that develop detectable technology. Not all intelligence is technological. Dolphins and elephants have sophisticated brains, but no radio transmitters. Perhaps technological civilization is a fluke, a peculiar path that evolution rarely takes. And L is the average lifespan of a technological civilization. This is perhaps the most important variable of all. A civilization that destroys itself after a century contributes nothing to the cosmic census. A civilization that endures for millions of years leaves traces across the galaxy. At the 1961 conference, the scientists plugged in their best guesses and arrived at estimates ranging from 1,000 to 100 million civilizations in our galaxy. Those estimates depended heavily on L. If civilizations typically last 10,000 years, the galaxy should be teeming. If they last only a few decades, if they inevitably destroy themselves shortly after discovering nuclear physics, then we might be alone. The Drake equation does not give answers. It shows us what we do not know, and what we do not know is staggering. In 1998, economist Robin Hanson published an essay that would fundamentally reshape how we think about the Fermi Paradox. He called his idea the Great Filter. Hanson's logic was brutally simple. We see no evidence of intelligent life in the cosmos, but given the vast number of opportunities for life to arise, statistically, we should see evidence everywhere. Therefore, something must be preventing the emergence of galaxy-spanning civilizations. Somewhere between raw physics and a species that conquers the stars, there is a step, or a series of steps, that is almost impossibly hard to pass. Hanson called this the Great Filter. Hanson listed 9 potential steps where the filter might be located. First, a star system must form with planets in the habitable zone. Second, self-replicating molecules must emerge. Third, those molecules must develop into simple single-celled life. Fourth, simple cells must evolve into complex cells with nuclei, eukaryotes. Fifth, eukaryotes must give rise to multicellular organisms. Sixth, those organisms must develop intelligence. Seventh, that intelligence must create technology. Eighth, that technology must become capable of colonizing other star systems. And ninth, that colonization must actually happen. At least one of these steps must be extraordinarily rare. So rare that across the entire history of the galaxy, almost no one passes through. Think of it like a series of trials that life must overcome. The formation of the right kind of planet, the origin of self-replicating molecules, the evolution of complex cells, the development of multicellular organisms, the emergence of intelligence, the invention of technology, the transition to a spacefaring civilization. Each step is a potential filter. The terrifying question is, where is this filter? If the Great Filter lies in our past, if the emergence of life, or the evolution of complex cells, or the development of intelligence is the extraordinarily rare event, then we are among the lucky few who have passed through. The universe is quiet because almost no one else has made it this far. But there is another possibility, one that should keep you awake at night. What if the Great Filter lies ahead of us? What if civilizations regularly reach our level of development, only to destroy themselves before they can spread to the stars? Nuclear war, biological weapons, artificial intelligence gone wrong, environmental collapse, climate catastrophe. Every day, our technology grows more powerful. Every day, our capacity for self-destruction increases. Perhaps this is the pattern throughout the cosmos. Intelligent species arise, develop world-changing technology, and then, before they can leave their homeworld, they annihilate themselves. Philip Morrison, one of the physicists at Fermi's famous lunch conversation, had worked on the Manhattan Project. He understood better than most how quickly a species could develop the means to end itself. At the 1961 Green Bank Conference, Morrison made a chilling observation. Humanity had developed global communication and interplanetary rockets. At roughly the same moment, it gained the ability to destroy itself completely. Perhaps all civilizations face this same convergence. Perhaps the filter is simply this: the window between developing the capability to be detected across the stars and developing the capability to destroy yourself is catastrophically short. This would explain the silence. The universe is not empty of intelligence. It is a graveyard of civilizations that burned too bright and died too young. But the Great Filter has another implication, one that should give you pause. Every time we discover something that makes the origin of life seem easier, the presence of organic molecules in interstellar space, the discovery of extremophiles that survive in conditions once thought lethal, evidence of ancient water on Mars, we should actually be troubled. Because if life is easy, if the early steps are common, then the filter must be somewhere else, somewhere ahead. Nick Bostrom, the philosopher who later proposed the simulation hypothesis, made this point with disturbing clarity. Finding life on Mars, he argued, would be terrible news. Not because life on Mars is inherently dangerous, but because of what it would tell us about our own future. If Mars had independent life, if abiogenesis happened twice in our own solar system, then the origin of life is probably common throughout the cosmos, which means the filter is not there, which means it awaits us somewhere on the path ahead. Conversely, if we search the solar system thoroughly and find it sterile, if we discover that Earth is truly unique, we can breathe easier. The filter is behind us. We have already passed the hardest test. The silent galaxy is full of barren worlds where life never emerged, and we are the exception. This is why the search for extraterrestrial life is not merely academic curiosity. It is an investigation into our own survival. Every discovery reshapes our probability of extinction. Every empty world is paradoxically good news. In 2000, geologist Peter Ward and astronomer Donald Brownlee published a book that challenged the optimism of the Drake equation. Its title was provocative: Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was simple but devastating. While microbial life might be common, perhaps almost inevitable wherever conditions permit, complex life, the kind that builds civilizations and wonders about the cosmos, requires an extraordinarily unlikely confluence of circumstances. Ward and Brownlee listed the requirements: a rocky planet in the habitable zone, a star stable enough to burn for billions of years, a large moon to stabilize the planet's axial tilt, a magnetic field to deflect cosmic radiation, plate tectonics to regulate the carbon cycle, a Jupiter-sized planet in the outer solar system to sweep away deadly asteroids, a location in the galaxy neither too close to the chaotic core nor too far from the enriched spiral arms. Each requirement on its own might not be unusual, but multiply them together and the probability plummets. The story of Earth begins to look less like a cosmic inevitability and more like an astronomical miracle. Consider the moon. 4.5 billion years ago, a Mars-sized body slammed into the proto-Earth, ejecting debris that coalesced into our oversized companion. Without that violent collision, Earth would wobble chaotically on its axis, making stable climates impossible. The same impact may have delivered water and enriched our planet with the heavy elements necessary for life. Consider Jupiter. The giant planet acts as a cosmic vacuum cleaner, its immense gravity capturing or ejecting the asteroids and comets that would otherwise bombard the inner solar system. Without Jupiter, Earth would have suffered far more devastating impacts, possibly sterilizing the surface repeatedly. Consider plate tectonics. The constant churning of Earth's surface buries organic carbon, regulates atmospheric carbon dioxide, and has likely prevented the runaway greenhouse effect, that turned Venus into a hellscape. We still do not fully understand why Earth has a plate tectonics, while Mars and Venus do not. Consider timing. Life on Earth emerged almost as soon as it possibly could, suggesting that microbial life may be easy. But it took another 2 billion years for eukaryotic cells, cells with nuclei, to emerge. Another billion years for multicellular life. These transitions may be agonizingly rare. The evolution of intelligence took even longer. For most of Earth's history, our planet was home to nothing more complex than bacteria. Complex life emerged only about 540 million years ago, in the Cambrian explosion. Dinosaurs dominated for over 160 million years without developing technology. Humans have existed for perhaps 300,000 years. We have had radio technology for barely a century. If you compressed Earth's history into a single year, human civilization would occupy the final seconds before midnight on December 31st. Ward and Brownlee suggested that while simple life might pepper the cosmos, complex life, animals, intelligence, civilization, could be extraordinarily rare, perhaps even unique. The rare Earth hypothesis does not say we are alone. It says that the universe may be full of microbial worlds, oceans teeming with simple organisms, planets covered in slime, but beings that build radio telescopes and wonder about the stars. Perhaps we are the only ones in the entire galaxy, perhaps in the entire observable universe. Critics of the rare Earth hypothesis have pushed back. Astronomer David Darling accused Ward and Brownlee of selecting only the factors that suit their case. After all, every planet is unusual in some way. The question is not whether Earth is unique, but whether its unusual features are actually necessary for complex life. And some of the requirements Ward and Brownlee identified have been challenged by subsequent discoveries. Europa, the ice moon of Jupiter, appears to have active plate tectonics beneath its frozen surface. Pluto, once dismissed as a dead world, shows signs of geological activity. Mars may have experienced tectonic activity in its past. Perhaps the requirements for complex life are more flexible than we thought. Perhaps evolution is more creative than our single example suggests. After all, we are extrapolating from an experiment with a sample size of 1. But the core insight of the rare Earth hypothesis remains powerful. We do not yet understand what is truly necessary for complex life to emerge. We do not know which of Earth's many peculiarities are essential and which are incidental. Until we find a second example, until we discover complex life elsewhere, we cannot know how rare we truly are. And there is something almost unbearable about the rare Earth hypothesis. If true, it means the universe is unimaginably vast and unimaginably empty. Billions of galaxies, each containing hundreds of billions of stars, each star potentially circled by worlds. And yet, in all that immensity, perhaps only one planet where beings look up at the night sky and wonder. The loneliness would be absolute, but so too would be the responsibility. In 2008, Chinese science fiction author Liu Cixin published a novel called The Dark Forest. In it, he proposed a solution to the Fermi Paradox, so chilling that it has since been discussed in academic papers and scientific conferences. The novel is the second book in Liu's Remembrance of Earth's Past trilogy, which begins with the three-body problem, a book that won the Hugo Award and has been praised by everyone from Barack Obama to Mark Zuckerberg. Liu's reasoning proceeds from two axioms. First, survival is the primary need of any civilization. Second, civilizations continuously grow and expand, but the total matter and energy in the universe remain constant. To these, Liu adds a third factor, the chain of suspicion. When two civilizations encounter each other, neither can know the other's true intentions. Even if you believe the other civilization is peaceful, you cannot know what they think about you. They might believe you are a threat, which would make them a threat to you. And even if both civilizations currently want peace, you cannot predict what either will become in a million years. Technological explosions can transform a primitive society into a galactic power in an eye blink of cosmic time. From these premises, Liu derives a terrifying conclusion. Imagine you're a hunter in a dark forest at night. It is utterly silent. You cannot see anything. You know that other hunters are out there somewhere, but you do not know their locations, their capabilities, or their intentions. If you encounter another hunter, what do? You cannot know if they are friendly or hostile. Even if they seem peaceful now, you cannot predict what they will become in 1,000 years or 1,000,000. Civilizations can undergo technological explosions, transforming from primitive to universe-threatening in a cosmic eye blink. The civilization that seems harmless today could become an existential threat tomorrow. Worse, the other hunter faces the same uncertainty about you. Even if both of you want peace, neither can be certain of the other's intentions. And in an environment where the cost of being wrong is extinction, the rational choice becomes clear. In the dark forest, there is only one thing to do. When you find another life, open fire. This is Liu's dark forest hypothesis. The universe is not silent because it is empty. It is silent because silence is survival. Every intelligent civilization has learned the same terrible lesson. To reveal yourself is to invite destruction. Those who broadcast their existence are eliminated. Those who remain are the quiet ones, the hidden ones, watching from the shadows. What does this mean for humanity? We have been broadcasting radio signals into space for over a century. Our television transmissions, our radar, our deliberate messages like the Arecibo transmission in 1974, all of these have been expanding outward at the speed of light, announcing our presence to anyone listening. If the dark forest hypothesis is correct, we have been screaming into the void, and something may have heard us. In 2010, the late physicist Stephen Hawking warned against attempting to contact extraterrestrial civilizations. If aliens visit us, he said, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. The dark forest takes this warning to its logical extreme. The most dangerous thing a civilization can do is make itself known, and we have been doing exactly that for a century. Critics of the dark forest hypothesis point out several problems. First, it assumes a particular kind of game theory, one where the costs of revealing yourself always outweigh the benefits. But this may not be true. Cooperation could be more advantageous than competition. Trade, the sharing of scientific knowledge, mutual defense against cosmic catastrophes. There are many reasons civilizations might prefer communication to extermination. Second, the dark forest requires a strange uniformity of motive. Not every individual within every civilization would have to agree with the policy of silence and preemptive strikes. It would take just one dissenter, one species that chose communication over concealment to break the pattern. Yet across the entire galaxy, across billions of years, no one has. Third, perfect hiding may be impossible. Advanced telescopes can detect biosignatures in exoplanet atmospheres. Industrial civilizations produce distinctive chemical pollutants. Megastructures like Dyson spheres would alter the light from their host stars. If you want to hide completely, you may have to stop developing entirely, which means you can never become powerful enough to threaten anyone. Still, the dark forest hypothesis has a visceral power that purely logical arguments cannot entirely dispel. We know from our own history how species treat each other. We know how colonial powers treated indigenous peoples. We know how our ancestors treated the Neanderthals. Perhaps the silence is not absence. Perhaps it is the sound of civilizations hiding. Perhaps it is the sound of something hunting. In 1973, astronomer John Ball of MIT's Haystack Observatory published a paper in the journal Icarus with a provocative title, The Zoo Hypothesis. Ball's premise was simple but unsettling. What if extraterrestrial civilizations are not absent at all? What if they are here, watching us, and have chosen not to make contact? Consider the analogy of a nature preserve. When we establish wildlife sanctuaries, we deliberately avoid interfering with the animals inside. We observe them, study them, but we do not disrupt their natural development. We do not march into the African savanna and introduce ourselves to the lions. Perhaps advanced civilizations treat younger species the same way. Perhaps they have decided that interference would disrupt our natural, cultural, and technological evolution. Perhaps they are waiting for us to reach a certain level of maturity before making contact. Paul suggested that the only way we can understand the apparent non-interaction between them and us is to hypothesize that they are deliberately avoiding interaction. This hypothesis has a variant known as the planetarium hypothesis, proposed by mathematician Stephen Baxter. What if the apparently empty universe is itself an illusion? What if we are living in a simulation, a cosmic terrarium, and our perception of an empty cosmos has been deliberately engineered? These ideas may sound like science fiction, but consider, if a civilization is millions of years more advanced than ours, their capabilities would be as incomprehensible to us as our technology is to an ant. They could observe us without detection. They could manipulate our perception of the cosmos. They could hide in plain sight. The zoo hypothesis presents a strange kind of hope. We are not alone. We have company. But our keepers have chosen, for whatever reason, to remain invisible. There is also a troubling implication. The zoo hypothesis requires what physicist Duncan Forgan calls galactic hegemony, a universe where all civilizations agree to the same non-interference policy. It would take just one civilization, or even one individual within any civilization, to break the silence, yet no one has. Either the universe is extraordinarily uniform in its ethics, which seems unlikely, or something else is going on. Perhaps the zookeepers are more like prison guards. Perhaps we are not being protected. Perhaps we are being contained. The zoo hypothesis has been seriously explored in scientific literature. In 2016, researcher João Pedro de Magalhães proposed a practical test. If advanced civilizations are indeed watching us, waiting for us to reach certain milestones before making contact, then perhaps we should explicitly invite them to respond. He suggested transmitting a message that acknowledges the zoo hypothesis, expresses our desire for contact, and argues that humanity is ready for inclusion in the galactic community. It would be, in essence, an application for membership. Of course, this assumes benevolent zookeepers. Other variants of the hypothesis are less comforting. The laboratory hypothesis, also proposed by John Ball, suggests that rather than observing us passively, advanced beings might be running experiments on us. Earth could be a petri dish. Humanity could be a research project. Even more disturbing is the possibility that the quarantine is not for our protection but for theirs. Perhaps we carry something, a pathogen, an idea, a tendency toward violence that the rest of the cosmos considers dangerous. Perhaps we are not in a zoo but in a containment facility. And there is one final unsettling thought. If we are being observed, how would we know? We assume that advanced technology would be detectable, that we would notice the surveillance drones, the monitoring stations, the probes in our solar system. But a civilization millions of years ahead of us might have capabilities we cannot imagine. Their surveillance could be invisible, integrated into the fabric of reality itself. We could be watched every moment of every day and never have the slightest inkling. The zoo hypothesis reframes the entire question of extraterrestrial intelligence. The question is not whether aliens exist. The question is whether they want us to know they exist. And if they don't, what could we possibly do about it? In 2018, researchers Anders Sandberg, Eric Drexler, and Toby Ord of Oxford University's Future of Humanity Institute published a paper with a provocative conclusion. They argued that the Fermi Paradox might not be a paradox at all. We might simply be alone. Their approach was different from previous analyses. Rather than plugging single estimates into the Drake equation, they used probability distributions to account for our uncertainty about each variable. They asked, given everything we don't know about the origin of life, the evolution of intelligence, and the development of technology, what is the probability that we are the only technological civilization in our galaxy? In the observable universe? The key insight was methodological. Previous analyses typically used best guess estimates for each variable in the Drake equation, then multiplied them together. This implicitly assumes we know more than we do. When you instead represent each variable as a probability distribution, acknowledging that FL, the probability of abiogenesis, could be anywhere from 1 to 10 NAR 30, the results changed dramatically. The answer surprised even them. When they ran their calculations, they found there was a substantial probability, roughly 1 in 3, that we are alone in our galaxy. The probability rose even higher for the observable universe. The authors titled their paper Dissolving the Fermi Paradox. Their argument was that the paradox only exists if we assume, without justification, that intelligent life should be common. Once we properly account for our uncertainty, the silence of the cosmos becomes entirely expected. There is no paradox. There is only the reasonable probability that we are first, or alone. The key insight was this: the Drake equation multiplies many uncertain factors together. When you properly account for the uncertainty in each factor, the tails of the distribution stretch enormously. You cannot rule out the possibility that the origin of life, or the evolution of intelligence, or the development of technology is so phenomenally rare that we are the first to pass through all the filters. Consider the origin of life. We still do not understand how the first self-replicating molecules emerged from raw chemistry. The probability could be high, or it could be vanishingly small. Some estimates suggest that the odds of abiogenesis, life arising from non-life, could be as low as 1 in 10 to the 30th power per planet per year. If the origin of life requires such an improbable event, then across the entire history of the cosmos, it may have happened only once, here on Earth. This is not because Earth is special. It is simply because we are observing from the only place in the universe where observation is possible. We are here because life arose here. If life had not arisen, no one would be asking why. The universe is 13.8 billion years old, but the conditions for life as we know it may have been hostile for most of that time. Early generations of stars produced few heavy elements. Galaxies were more chaotic, bathed in radiation from active supermassive black holes. The heavy elements necessary for rocky planets, for organic chemistry, for life, took billions of years to accumulate. Perhaps we are not late arrivals. Perhaps we are among the first. The astronomer Adam Frank and astrophysicist Woodruff Sullivan published a paper in 2016 exploring exactly how pessimistic we need to be about the probability of intelligent life to explain our cosmic solitude. They found that even if the probability of a technological civilization arising on a habitable planet is just 1 in 10 trillion, a number so small it defies intuition, there should still have been at least one other civilization in the history of the observable universe. But there is a catch. That civilization would not necessarily be anywhere near us. They might be billions of light years away, in a galaxy we have never examined, extinct billions of years before Earth even formed. We would never detect them. They would leave no trace that could reach us. This points to an important distinction. The Fermi Paradox is sometimes framed as, where are the aliens? But the stronger version is, why has no one colonized our solar system? A civilization that merely broadcasts radio signals might be undetectable, but a civilization that spreads, that builds, that transforms its corner of the galaxy, that should leave evidence we cannot miss. Unless, of course, something always stops them. Think about what this means. The first technological civilization in the galaxy, or perhaps in the entire observable universe, would face exactly the situation we face now. They would look out at a cosmos full of stars, full of planets, full of potential, and see nothing but silence. They would wonder where everybody is. They would develop theories about great filters and dark forests and sleeping ancients. They would not realize, could not realize, that they were the answer to their own question. They were first, and there was no one to greet them. Astrophysicist Avi Loeb of Harvard has developed this idea further. The cosmic conditions for life have not been constant. The early universe was too hot, too violent, too radiation-soaked for life as we know it. Heavy elements had to be forged in the hearts of stars and scattered by supernovae before rocky planets could form. Galaxies had to calm down, their central black holes quieting after their early feeding frenzies. Loeb calculated that the probability of life emerging increases as the universe ages. We may be living in the first era when life is truly possible at scale. The silence is not because civilizations destroy themselves or hide or sleep. It is because we are the pioneers. If so, the responsibility is almost incomprehensible. Every choice we make echoes across the future of the cosmos. If we destroy ourselves, there may be no one to take our place for billions of years, if ever. If we survive, if we spread, if we seed the galaxy with intelligence, we become the ancestors of everything that follows. We would be the old ones that future civilizations wonder about, the first movers, the founders of something unimaginably vast. This solution to the Fermi Paradox carries an enormous weight of responsibility. If we are first, then the future of intelligence in the cosmos depends on us. Every decision we make, every crisis we survive or fail to survive, determines whether the universe will ever know consciousness at all. We are not just observers. We are the vanguard, and the cosmos is waiting to see what we do next. In 2017, Anders Sandberg, Stuart Armstrong, and Milan Cirkovic proposed one of the most unusual solutions to the Fermi Paradox. They called it the estivation hypothesis. It comes from the word estivation, which means dormancy during hot or dry periods, the opposite of hibernation. Their argument proceeds from thermodynamics. Imagine a civilization that has converted itself entirely to digital form. They no longer have biological bodies. They exist as patterns of information running on unimaginably powerful computers. For such a civilization, the most precious resource is not energy or matter. It is computation. And here is the key insight. Computation is more efficient at lower temperatures. This is not speculation. It is physics. Landauer's principle, formulated in 1961, states that erasing one bit of information requires a minimum amount of energy that depends on temperature. The colder the environment, the less energy you need per computation. Right now, the cosmic microwave background radiation keeps the universe at about 2.7 Kelvin, just a few degrees above absolute zero. But the universe is expanding and cooling. In trillions of years, the background radiation will be orders of magnitude colder. Sandberg and his colleagues calculated that a civilization waiting until the far future could perform 10 to the 30th power times more computations with the same amount of energy. That is a 1 followed by 30 zeros. A million, trillion. For a digital civilization whose existence consists of computation, of thought, of experience, of whatever post-biological minds do, waiting is not a sacrifice. It is an investment. A few trillion years of sleep, and then an eternity of unimaginable computational abundance. The estivation hypothesis suggests that advanced civilizations have already explored the galaxy. They have already gathered the resources they need, and now they are sleeping, waiting for the cosmos to cool, for the optimal conditions to awaken and begin their true existence. We do not see them because they are inactive. Their infrastructure is dark. Their probes are dormant. They have settled in for a cosmic nap. If this hypothesis is correct, the universe is not empty. It is a cemetery of sleeping giants. Ancient civilizations older than our sun lie dormant in the void, patient as mountains, waiting for an eternity we cannot comprehend. And perhaps one day they will wake. The estivation hypothesis has some testable implications, which is more than can be said for many Fermi Paradox solutions. If ancient civilizations are preserving resources for the far future, they might intervene to prevent natural processes that would waste those resources. We should look, Sandberg suggests, for unusual phenomena. Galaxies that seem to avoid collisions with their neighbors, regions where massive stars fail to form, since massive stars burn through their fuel quickly. Areas where galactic winds seem unusually suppressed. These would be signs of cosmic engineering, beings manipulating their environment on scales we can barely imagine. We see no such signs. The cosmos appears to operate according to ordinary physics, with no evidence of intervention. This counts against the aestivation hypothesis, but it does not disprove it. Perhaps the aestivators are more subtle than we expect. Perhaps their modifications are too small to detect with our current instruments. Perhaps they have deliberately left our region of space undeveloped, a cosmic wilderness preserve. Or perhaps, and this is where it gets truly unsettling, perhaps they have defense mechanisms. Perhaps any young civilization that begins to spread to threaten their dormant resources is quietly eliminated. Sandberg himself notes this disturbing implication. If we were to launch self-replicating probes to colonize the galaxy, and if aestivators exist, we might trigger their security systems. Their robotic guardians might wake just long enough to deal with the threat, then return to their long sleep. We might never know they were there until it was too late. This is science fiction territory, of course, but the aestivation hypothesis reminds us that we cannot assume advanced civilizations think like we do. Their timescales, their values, their very conception of existence might be utterly alien. A species that measures its plans in trillions of years might not even register our fleeting civilization. We are mayflies wondering where the gods are. The gods are dreaming, and their dreams last longer than our entire species' existence. In 2003, philosopher Nick Bostrom of Oxford University published a paper in the Philosophical Quarterly that has haunted thinkers ever since. His title was a question: Are you living in a computer simulation? Bostrom's argument was not that we definitely live in a simulation. His argument was more subtle and, in some ways, more disturbing. He proposed a trilemma, a logical structure that forces you to accept one of three uncomfortable conclusions. Bostrom's argument was structured as a trilemma. He claimed that one of the following three propositions must be true. 1. Civilizations almost always destroy themselves before developing the technology to create highly detailed simulations of conscious beings. 2. Civilizations that reach this technological level are almost universally uninterested in creating such simulations. 3. We are almost certainly living in a simulation right now. The logic is straightforward. If civilizations commonly survive to develop sufficient computing power, and if some non-trivial fraction of them choose to run simulations of their ancestors, simulations detailed enough that the simulated beings believe themselves to be real, then the number of simulated beings would vastly outnumber real, biological beings. Consider the math. A single post-human civilization might run billions of ancestor simulations, historical recreations, sociological experiments, entertainment. Each simulation might contain billions of conscious beings. Across all post-human civilizations in the universe, the total number of simulated minds would dwarf the number of biological minds by factors of trillions or more. If you do not know whether you are simulated or real, and if simulated beings are astronomically more common than real ones, then probability alone suggests you are probably simulated. What does this have to do with the Fermi Paradox? If we live in a simulation, the silence of the cosmos may be by design. Our simulators may not have bothered to render a universe full of aliens. Why would they? Simulating an entire galaxy full of civilizations, each with billions of conscious beings, would require astronomical computing resources. It is far simpler to render a universe that appears empty, a lonely stage for whatever experiment they are running. The silence is not evidence that aliens do not exist in true reality. It is evidence that our simulators chose not to include them. This is, of course, impossible to prove or disprove. That is what makes it so unsettling. We cannot step outside the simulation to verify our reality. We cannot examine the source code. We can only look at the world we see and wonder, is any of this real? The simulation hypothesis also raises questions about the nature of our simulators. Are they running a historical recreation, a sociological experiment, a game? Are we their ancestors, their entertainment, their science project? And here is the darkest thought of all. If we are simulated, what happens when the simulation ends? When the researchers turn off the machine and go home for the night? Some physicists have attempted to find evidence for or against the simulation hypothesis. If our universe is a simulation, there might be artifacts, rounding errors, pixelation at very small scales, processing constraints that limit the simulation's fidelity. In 2012, physicists Silas Bean, Zohre Davoudi, and Martin Savage proposed looking for constraints imposed by a discrete space-time lattice. If the universe is computed on a grid of some kind, certain high-energy cosmic rays might show subtle directional preferences. Their paper sparked both serious interest and considerable skepticism. Others have noted that quantum mechanics itself, with its inherent randomness, its superposition of states that collapse only when observed, behaves exactly as you might expect from a simulation optimized to avoid rendering things that aren't being looked at. But here is the problem. Any evidence we find within the simulation. Any physics we discover is the physics of the simulation. We cannot step outside our reality to examine it from the outside. We are characters in a novel, trying to deduce whether we are characters in a novel. The simulation hypothesis is not strictly about the Fermi Paradox, but it offers a clean resolution. The silence is intentional. It was coded into the simulation from the beginning. Our simulators, for whatever reason, chose to create a lonely universe. Perhaps they wanted to see how a civilization responds to isolation. Perhaps they wanted to study our psychology, our philosophy, our desperate search for meaning in an empty cosmos. Perhaps they find it aesthetically pleasing, this single spark of consciousness in an infinite void. Or perhaps, and this is the most vertiginous possibility, perhaps our simulators are themselves asking where everybody is. Perhaps they are simulations within simulations, turtles all the way down, an infinite regress of lonely universes nested within each other. We cannot know. That is what makes the simulation hypothesis so maddening. It explains everything and nothing. It offers no path forward, no way to test it, no way to escape it. All we can do is continue living as if reality is real, which functionally is exactly what beings in a simulation would do. Let us return to that summer afternoon in 1950. Enrico Fermi, fork in hand, staring at his colleagues, asking a question that no one could answer. Where is everybody? We have now explored 7 possible answers. The Great Filter suggests something prevents civilizations from reaching the stars, and it may lie ahead of us. The rare Earth hypothesis proposes that complex life is fantastically rare, making us cosmically precious. The dark forest theory warns that the universe is hostile, that silence is survival, that broadcasting our existence is suicide. The zoo hypothesis suggests we are being watched by unseen overseers who have chosen not to reveal themselves. The We Are First hypothesis proposes that we are pioneers in a young universe, the vanguard of intelligence itself. The estivation hypothesis suggests the ancients are sleeping, conserving their resources for a future we cannot imagine. And the simulation hypothesis raises the possibility that none of this is real at all. Each answer is terrifying in its own way. The Great Filter threatens extinction. The dark forest threatens annihilation. The zoo threatens our free will. We Are First threatens us with cosmic responsibility. Estivation threatens us with irrelevance. And the simulation threatens our very sense of reality. But there is something else worth noting. These solutions are not mutually exclusive. The truth might be a combination of several of them. Perhaps the Great Filter exists, but it lies in our past, in the rare emergence of eukaryotic cells, or the even rarer origin of life itself. Perhaps the universe is also a dark forest, with civilizations that pass the filter hiding from each other. Perhaps some of those hidden civilizations are also running simulations. Perhaps we are in one of those simulations, created by estivating beings who wanted to model the early universe while they sleep. The truth is likely more complex than any single hypothesis. The universe is vast enough to contain multitudes, but there is another possibility we have not considered. Perhaps none of these solutions is correct. Perhaps the answer is something we have not imagined, something beyond our cognitive abilities to conceive. After all, we are a young species. We have been listening to the cosmos with radio telescopes for barely 70 years, a fraction of a cosmic second. Our instruments are still primitive. Our understanding of life is based on a single example: ourselves. Perhaps intelligent life exists in forms we cannot recognize. Organisms that think on timescales of millennia. Minds that exist in the plasma of stars. Entities that communicate through gravitational waves or dark matter or phenomena we have not discovered. Perhaps they have been trying to contact us and we simply lack the senses to perceive them. Or perhaps the answer is simpler. Perhaps the universe is large enough to contain all these explanations, each true in different places and times. Some civilizations destroy themselves, others hide, others sleep, others watch, and somewhere out there, others are just waking up as we are, looking out at the silent stars and wondering the same thing Fermi wondered on that summer afternoon. Where is everybody? We do not know. Not yet, but we are searching. In observatories around the world, in the data streams of space telescopes, in the equations of physicists and the speculations of philosophers, the search continues. Every year, our instruments grow more sensitive. Every decade, our reach extends. The James Webb Space Telescope is now studying the atmospheres of exoplanets, searching for the chemical signatures of life. The Breakthrough Listen initiative is scanning millions of stars for radio signals. The search for extraterrestrial intelligence has never been more sophisticated. Since the Green Bank Conference in 1961, we have learned an extraordinary amount. We know that planets are common. Nearly every star has at least one. We know that rocky planets in habitable zones number in the billions. We know that the building blocks of life, amino acids, sugars, organic molecules, pervade the cosmos. We have found extremophiles on Earth that survive conditions once thought lethal. And yet, the silence persists. SETI, the search for extraterrestrial intelligence, has now been running for over 60 years. Frank Drake's Project Ozma in 1960 pointed a radio telescope at two nearby stars for a few weeks. Today, the Breakthrough Listen project scans millions of stars across billions of frequencies. The sensitivity of our instruments has increased by factors of millions. Nothing, no clear signal, no obvious artifact, no message in a bottle drifting through the void. Some argue this tells us something profound. If there were technological civilizations in our cosmic neighborhood, we should have detected something by now. The silence grows more significant with each null result. Others counter that we have barely begun to search. The galaxy is vast, the electromagnetic spectrum is wide, and we cannot know how alien signals might be encoded. We are looking for a particular kind of technology, radio transmissions like our own, and assuming that advanced beings would use something similar. This may be profoundly naive. Perhaps they communicate through gravitational waves, or neutrino beams, or quantum entanglement, or phenomena we have not yet discovered. Perhaps they encoded their message in the structure of the cosmic microwave background radiation. Perhaps they are trying to contact us, and we lack the senses to perceive them. One day, we may find an answer. It might be a signal, a clear mathematical pattern in the static, proof that we are not alone. It might be silence that continues for centuries, confirmation of our cosmic solitude. It might be a probe from a sleeping civilization, drifting through our solar system. It might be contact or invasion. Whatever the answer, it will change everything. If we find others, we will know we are not unique. The universe is a community, not a void. Our art, our music, our philosophy, our science, all of it will have context in a cosmic conversation. We will know that intelligence can survive, can spread, can endure. We will have proof that the great filter, if it exists, lies in our past. We will also have to reckon with the fact that we are not special. Every assumption of human exceptionalism, every religious tradition that places humanity at the center of creation, every philosophy that treats Earth as unique, will have to be revised. This could be liberating or devastating, depending on who you ask. If we find only silence, we will know we are precious beyond measure. The entire weight of intelligence, of consciousness, of meaning in the universe rests on our shoulders. Everything humanity creates, everything we achieve, everything we become matters not just for us, but for the cosmos itself. We will also have to reckon with our aloneness. There will be no one to help us, no one to save us, no one to learn from. If we destroy ourselves, there may be no one to take our place. If we survive, we do so entirely on our own. Either way, the stakes could not be higher. Fermi died 4 years after that lunch conversation, of cancer at age 53. He never lived to see the exoplanet revolution, the Voyager missions, the search for biosignatures on Mars. He never knew how his casual question would echo across generations. But we carry his question with us into every observatory, every laboratory, every rocket launch. We carry it in our DNA, this ancient curiosity about our place in the cosmos. Where is everybody? Tonight, when you look up at the stars, remember that every point of light is a sun, many with planets, some with worlds that might, even now, harbor life. Remember that the silence is not nothing. It is a message, encrypted, waiting to be decoded. Remember that you are part of the only species we know of that asks these questions, that you exist at a moment in history when we might, for the first time, find an answer. And remember, the most terrifying possibility of all is not that we are alone in the universe. It is that we are not. There is one more thing I have not mentioned. One possibility that does not fit neatly into any solution, but that haunts this entire discussion. What if we already have the answer and we simply refuse to accept it? Every solution to the Fermi Paradox ultimately reflects our own anxieties and hopes. The Great Filter speaks to our fear of extinction, the dark forest to our suspicion that the cosmos is hostile, the zoo hypothesis to our desire to be special, to be watched, to matter, the simulation hypothesis to our growing unease with technology. We are first to our ambition and our sense of cosmic destiny. Perhaps the paradox is not about aliens at all. Perhaps it is about us, about our place in the cosmos, about our need for meaning in an apparently meaningless universe. Carl Sagan, that young graduate student at the 1961 Green Bank Conference, who would go on to become the world's most famous astronomer, understood this better than most. He spent his life searching for extraterrestrial intelligence, and he never found it. But he kept looking, not because he was certain something was out there, but because the search itself was worthwhile. The cosmos is within us, Sagan said. We are made of star stuff. We are a way for the universe to know itself. Whether we are alone or surrounded, first or last, observed or ignored, simulated or real, this remains true. We are the cosmos become conscious. We are matter that asks questions. We are the universe looking back at itself and wondering, perhaps that is enough? Perhaps the answer to Fermi's question, where is everybody, is simply, here. We are here, and we are listening. The Arecibo radio telescope, which Frank Drake used for his pioneering SETI observations, collapsed in 2020. Its iconic dish, which had listened for alien signals for decades, crashed into the Puerto Rican jungle. But new telescopes have risen to take its place. The square-kilometre array, currently under construction in Australia and South Africa, will be the most sensitive radio telescope ever built. China's vast telescope, with a dish the size of 30 football fields, is already scanning the heavens. The search for extraterrestrial intelligence continues with tools Frank Drake could barely have imagined. Machine learning algorithms sift through petabytes of data. Optical SETI programs search for laser pulses. Astrobiology missions probe the moons of Jupiter and Saturn for signs of life. Within your lifetime, we will search more stars, more frequencies, more modalities than in all of previous human history combined. We will analyze exoplanet atmospheres for biosignatures. We will send probes to the ocean worlds of our own solar system. We will peer deeper into the cosmos than ever before. The search continues, and somewhere, perhaps, a signal waits. A message in a frequency we have not yet checked, from a star we have not yet examined, from a civilization that has been broadcasting for millennia, waiting for someone to listen. Or perhaps the silence will continue. Perhaps we will search the entire galaxy and find only echoes of our own loneliness. Perhaps we will never know the answer. Perhaps the question is the point. Tonight, when you look up at the stars, remember, every point of light is a sun. Many have planets. Some of those planets are worlds. And on some of those worlds, something might be looking back. We are listening. Are you out there? Where is everybody? We do not know. We will never stop asking. In the silence of space, in the static between the stars, in the vast emptiness that stretches from here to the edge of the observable universe and beyond, somewhere out there, perhaps, an answer waits. We just have to be brave enough, patient enough, persistent enough, and curious enough to find it. That is what it means to be human, to ask the questions even when the answers might be terrifying, to search the cosmos even when the silence seems endless, to wonder about our place in the universe even when wondering offers no comfort and no certainty. 75 years after that summer afternoon in Los Alamos, Fermi's question still echoes across the cosmos, and we are still listening. The search continues. It will always continue until we know, until we understand, until the silence finally breaks, or until we finally accept that the silence is the answer. Either way, the question remains beautiful, terrifying, haunting, and utterly, profoundly eternal. Where is everybody? We are here, Enrico. We are still looking. We are still wondering. We are still listening. We are still human. And someday, perhaps, we will finally find out. The stars are waiting. And so, with patience and wonder and boundless hope, are we